Thanks everybody for coming. This is the Pipelines on HPC workshop. My name is Sam Friedman. I work at the YCRC. That's the Center for Research Computing. We're in charge of all of the computing clusters on campus. And yeah, this is going to be the second time we've given this workshop. So it's still very much looking for your input. At the end of the workshop, we have a little QR code and URL that pops up. If you wouldn't mind, before you leave, just doing a quick 2-minute feedback survey. Really helps us, develop the workshops and make sure that they're useful to everyone. So today we're going to be going over a good amount of. Make sure still on. There we go. We're going to be going over a few different ways to approach the topic. The topic, of course, being software pipelines. How do you go from a script that works for your analysis to something that is reproducible and transferable? And what are the kind of software tools we have available to us to help do that? So we'll start with just introducing the problem, talking about some more theoretical concepts and sort of baseline concepts of pipelining and why things are designed the way they are. And then I've built an example workflow that is kind of a stand-in for the type of data work that you may do in your day-to-day work. That allows us to sort of look at something that is digestible and runnable in a workshop context and still take all of those concepts forward to your work. We'll be first approaching that from the context of Bash, so ordinary Linux shell scripts, and Slurm, running that on the clusters. Then the first specific tool we'll look at is called Snakemake. We'll be re-engineering, I'd say, the example workflow into a Snakemake pipeline and showing how that works and the sort of things that we like to keep in mind when we're trying to take what we have and make as few changes as possible to get something useful out of a tool like Snakemake. I'll take a brief break at that point before I start talking about Nextflow. And the way that I approach Nextflow in this course is it's very similar to Snakemake. We talk about the sort of side-by-side differences from going from this tool Snakemake to the tool Nextflow. Difference largely being that Nextflow is a little more complex. And so I spend most of the time trying to focus on using pipelines that already exist, that are present in the research community, things like open source pipelines, things like the NF Core ecosystem. But of course, there will be resources available if you want to look into building your own Nextflow pipelines, but we don't go into the same custom level as we do for Snakemake. So to start, just a little bit of setup, and I just want to note that you can just go to this URL if you ever need. The slides are there as well. If you want to follow along, all of the code for the examples are there. And if you want to follow along, and we have a couple points where we're going to stop and do some hands-on examples. These are all in here, and you can run this on the cluster, or you can run the non-Slurm examples locally as well if you have your environment set up. So I'd recommend logging into one of the clusters. I've designed all of this to work on the login node. So usually we ask you, hey, please, stay off the login node if you're doing real work. In the interest of making sure everyone is not waiting on queues to get a job assigned during the workshop, all the actual examples are super lightweight, so they should work fine on the login node, so don't worry about that. And that way you don't have to wait. You can see I have on the main screen my slides. I also have over here on a side screen VS Code instance. I'm going to be using this just sort of to run through the examples once everyone has had some hands-on time with them. And then I have a couple sort of me-only demos that are more like, things that are difficult to get 20 people to run at the same time, like automating these over Slurm jobs and things, but that I still want to illustrate. So I'll be doing sort of some of that for there on that screen. And both of these should be captured in the Zoom recording as well. So me and Agata did some groundwork to make sure that would work, but it will be on the Zoom recording. Okay. So yeah, if you're still working on downloading the workshop repository, I recommend just copy that URL and throw that up into your browser so you can view the repository as well, and I can move on with the slides. All the same instructions are on the repository README. Okay, so let's begin with some theory. So the problem that I wanted to talk about today, and really what the purpose of this workshop is to talk about a better way to automate and handle and distribute data workflows, data pipelines. So if you work at all with any kind of analysis of data or statistics or generating figures from data, you're probably very familiar with this kind of pipeline. You start with, maybe there's a step that intakes some raw data from an instrument or from an experiment. It does some sort of processing. Maybe it's an R script. Maybe it's some custom C that you wrote that creates a clean data set. And then from that clean data set, you run some analysis. Maybe you're doing statistics. Maybe you're aggregating and summarizing. And then finally, when you have all of that finished, you make some figures or create a final data table or something deliverable that you'll be using for the actual results of your science and of your experiments. This workflow is awesome. And if you do this, if you have these kinds of steps, separated and they're in script files and you know how to edit them and run them and teach other people how to edit them, you're already actually kind of ahead of a lot of people, I think. And when it comes to managing your research data and the pipelines that operate on your data to produce your results. What I want to talk about with this workshop is how can we do better than this? And what tools exist for us to do a little bit extra work, not much, and as a result, get a lot of extra useful things out of it. Things like better reproducible,ity better traceability of how long our steps in our pipelines are taking. And of course, the answer to this is tools like Snakemake and Nextflow. So when you're just operating sort of ad hoc, with just a handful of scripts, there's a lot of things that can be difficult. You can have a bunch of different versions of scripts. Maybe you get some revisions back for a paper, and suddenly you have to make a version 2 or version 2.1-final-for real this time of all of your scripts, right? You can need to run the same pipeline on a bunch of different data, new samples, new collaborators have data they want you to run your scripts on, and so you have a bunch of duplicated data folders. Maybe you need to work with a collaborator, and what works on your machine doesn't work that easily on their machine. And then maybe a step fails halfway through the pipeline. How do you know if the output that it processed until then is valid? And how do you track whether you need to reprocess the entire pipeline or just what failed? So a lot of what we're going to be going over today is going to start with just the sort of key concepts for what do you keep in mind when you're constructing a data pipeline, and what are some of the things that we think about when we try to plan out a pipeline for data analysis so that it can be amenable to these concepts. We will go over a simple example workflow, like I mentioned, that uses bash scripts and Slurm. That's sort of our sort of step zero ground level example. And then from that example, we will build on top of it into a Snakemake pipeline. And from the Snakemake pipeline, we'll then also touch a little bit on the differences between Snakemake and Nextflow, which is a similar tool for pipelining, and a bit more about pipelines that exist in the community, open source, that you can take advantage of. So to start, I want to talk about how a pipeline is organized from a sort of a graph theoretic point of view. When we talk about a pipeline, we're talking about data flowing from beginning to end through a number of different steps. And in this case, we define our workflow as what is called a directed acyclic graph. It is directed because we can draw arrows that have direction from one task to the next. And in this case, all of the tasks, the concrete steps that we do to operate on our data is one of these nodes. So it could be step A, B, C, or D. And the edges between them are our dependencies. So in this case, we would read this graph as saying step B depends on the data from the input task, and step D depends on the data from step B. We call this an acyclic graph because this only works if there are no cycles or loops in the graph. So if step D depends on the results of step B, we can't also have step B depend on the results of step B, because that creates a loop. So the idea being, if we define our workflow in a way that it has these properties, and it can be represented as a directed acyclic graph, which everyone calls DAG. So if we can define our workflow as a DAG, we get a lot of really interesting things for free that these tools are built to do really in a very optimized and fast way. And I'll be showing some of the very nice things that we get out of this. So this is what our workflow looks like. I also want to talk about some of the properties of the individual tasks in the workflow. So each of these nodes also have properties that, if we design them properly, can help us make a really useful, very fast and reproducible pipeline. So the one thing that I want to touch on, although there's a lot of theory that we could go into, is atomicity. So in each step of the pipeline, it has the property of being what's called atomic. This means essentially that the step can be thought of as binary. It either completely succeeds or it completely fails. And we know whether it has failed or succeeded. So if a step fails, it shouldn't produce partial output. Imagine this like we have maybe 100 samples and we have a bunch of things we want to do. Maybe the first step for each of these 100 samples is, in the life sciences context, it could be maybe aligning to a genome. If our step was aligned to the genome for 100 samples, it would be possible for one of these 100 samples to fail, and then we're not sure what the state of our entire task is, this entire step of the pipeline. Is it successful because it completed 50 of the 100 samples, or did it fail because it has failed at step number 55 out of 100? So the idea with designing a step to be atomic is that we should instead split this aligning step, as it were, into individual steps where it can only ever succeed or fail. So instead of one step that runs 100 alignments, we would have 100 steps that each run their own alignment. And that means that eventually we can build this large directed acyclic graph for each of these steps and hand it off to one of the pipeline tools that we'll see and have it just handle everything for us. Do all the tracking, do all of the resuming as we need it. So a big part of science is not just completing the workflow and completing the experiment, but it's, of course, making the experiment and making the science reproducible. So when I say reproducible, I typically mean that the same input with the same options should produce the same output. And this is a great thing. We want this to be what's called portable, meaning if it works for us, it should work for someone else, providing they have the same tools, and no matter what their underlying system is. We want to be able to version control our pipeline, not just our analysis. So a lot of journals I've noticed have begun asking for code artifacts with your paper. So a lot of the times they want you to know that yes, your individual scripts, like let's say you have the R script that produces your figures. Of course, that has been in version control in Git, but they want to ensure that given a artifact of your code, it can run from the raw data all the way through to your results in a single pipeline. That is, it can be reproduced on their machine. And pipelining tools like this are a big part of what makes that easy to do and easy to track. Now, finally, when I've been mentioning that when you use a pipelining tool like the ones we're talking about today, you get a lot of really nice features for free. You get things like logging so that you know exactly what step was run on what piece of data, in what order, with what parameters. And that's not just useful for your debugging, but also to help you provide reproducibility information for colleagues and other people that may want to investigate and reproduce and build upon your work. So that's the sort of the basic theory of why we care about these kinds of properties and these kinds of designs for data pipelines. And now I'm going to talk about the example that we'll be working on today. So I put this example together to represent what is for you maybe some output from a simulation. It may be genomic data or some experimental data from a lab. In our case, we have 10 data files. They are the full text of the plays of William Shakespeare, just my 10 favorite plays. And in this case, they are all UTF-8 encoded plain text files, so just normal text with some characters, punctuation. And in this case, the idea of this is that it's a small enough data set that we can run it in a workshop in the handful of hours we have here together. But all the tools that we use and all of the things that we consider when we're working through this example scale up to the real data that you'll be working with. So in our case, we have these 10 plays from Shakespeare. And the goal for each of the plays is we want to compute a measure of similarity between each pair of plays based on their most common words. So for a toy example, this means that we have a number of steps. And just like when you are developing a data pipeline for your own work, it can be very helpful to sort of enumerate out what the steps should be to go from the raw data to the final deliverable that you want. In our case, at the very end, we want a table, a CSV file, of the similarity scores between each pair of plays. So the way the workflow will run is we will start by cleaning each play. We'll be removing punctuation, symbols, extra spaces, and we'll make sure everything is in lowercase characters. Step 2, we'll count the frequencies of words so that we can rank them, extract the top 100 words in each play at step 3. Then we'll compute what's called the Jacquard similarity, a very simple measure of text similarity between two corpuses on step 4. And finally, 5, combine all those outputs into the similarity matrix. So the way that this looks, if we draw it out, I had talked about a directed acyclic graph, and this is the DAG for our, a subset of our Shakespeare play example. So if we start with 2 plays, for example, here we have Hamlet.txt and Macbeth.txt. They work through the clean step, the count word step, the top 100 step. They then go both together into the compare step and eventually produce the similarity matrix.csv. So we can kind of already start to see how the architecture of our pipeline lends itself to one or the other processing approach. So the compare step has 2 arrows going to it. That means that it's dependent on 2 outputs from previous steps, whereas the top 100 back to count words, back to clean, back to the input play is just sort of a straight pipeline. And once you see enough of these, you start to associate that when you see just a straight pipe like that, that means that that entire chunk is totally parallelizable. It doesn't matter. It doesn't have any dependencies to other parts of the pipeline, doesn't have dependencies to other data. And so when we start thinking about how can we speed this up, how can we make this go as fast as possible, part of the advantage of designing things like this is that we can sort of run all of the parallel parts together, and then the compare step only needs to wait for each of the parallel parts to finish. But this is only 2 plays. So if we look at the sort of the larger DAG, and I realize you can't really read that, but the idea is that this fan out here, which is what we call when the number of interdependencies suddenly increases. Now we have 45 pairs that we need to compare. And you can see how what was once a simple parallel pipeline, once it gets to the compare step, suddenly has a lot of interdependencies. And so where we would originally need to define each of these interdependencies and define these combinations ourselves in our scripts, we're going to be using these pipelining tools, starting with Snakemake, to help manage this and run this pipeline in a really convenient and easy way. So I have a few bash scripts here in the workshop repository. It's not, we're going to be going over sort of all the operative parts of them. So feel free to look through them, and I'm about to step through a bunch of them on screen. But just know that each step I have split out into its own script. So the first one is called Analyze Play, which contains clean text, count words, and extracting the top 100. The next one is Compare Plays, which computes the similarity score between them, and then Combine Results, it creates the CSV file from those outputs. And then I wrap that all together in this little run all script that runs everything in order. And over on the side screen, I'm going to take a open here, and you can see that the script here is exactly sort of what I was describing before. I have it organized out here with step 1, cleaning the text, step 2, counting word frequencies, and so on. And we're going to be going over in the next few slides what these individual commands are doing and how we're going to be translating those a little bit into Snakemake. So the idea being that when we have all of our scripts set up, scripts ready to go, we have, where's my notes? So just as before, I'll give now an actual concrete example. In the Hamlet case, we have the line, "How now, Ophelia? What's the matter?" After the clean step, we have now a list of words that have been normalized to all lowercase, all punctuation and spaces removed. The count step then gives us a ranked list of the number of appearances of each word. The articles and prepositions come first, and then the word sounds appears once at the end. And then we just clip that to the top 100. We do this for all 10 plays. Then we take each of these plays. The Jacquard similarity is just the ratio of the number of words in common between two sets over the total number of unique words in those two sets. So in this case, 72 divided by 128, it gives a similarity score of 0.563. So that'll be the score for the Hamlet-Macbeth pair. We want to do this for all 45 pairs. And then the combined results script is going to loop through all of the similarity files, which just store the score from the previous comparisons, creates us a output CSV file. Cool. So I mentioned that we have this little orchestrator loop, and this is really the sort of the baseline as what I would expect someone to automate using just bash. So let's say you had all of these data files, you had all of these steps in the scripts ready to go, you've tested them, you know that it works for your plays, and now you want to run it for all of the data you have, in this case, all 10 plays. So you might come up with something that looks kind of like this. You have step one is analyzing all the plays. So you run the analyze play script for each of the plays in your data directory. Step two, once all those are done, you can compare the pairs. So you have now the data, everything.txt is in the data, and then you need to index each one to create pairs that don't repeat. So you do a couple nested for loops there. And then at the end, you have the combined results script, which is just finding all the outputs from step two, combining them into a table. That works fine, but there are definitely some ways that it can be improved. So for one, everything that we just saw in that script runs serially. There's not yet any parallelism happening here. So where we are comparing all the pairs in step two, let's say that is, maybe it's a very expensive step. It takes a while. Maybe it takes 40 minutes or an hour to do one of these comparisons. Well, in our case, we're just running them one after the other without any real separation and parallelization to be able to speed this up. We also have no real dependency tracking in a simple bash script. If one of these steps fails, our script might fail, or it might continue to run the downstream steps anyway, which will produce data that doesn't mean anything to us. It's just sort of a waste. It makes it more difficult to debug. Also, there's no checkpointing. If one of these steps fails, we have to start from scratch again. And of course, we have to manually clean up any intermediate files that we've saved. All of this can certainly be solved in bash. You can write more bash code that will, split things out and run them as separate SBatch jobs on the cluster. You can write code that manages failure checks and sees if the output files exist or not. And you can write checkpointing code. The point of using a tool like Snakemake or like Nextflow is that it reduces the amount of code that you need in your workflow to the things that are relevant to your science, the things that are actually working to produce output from your data without the sort of additional cruft of handling all of these issues. You can leave that to the tool itself. So I want to start here. We're going to run just the original bash pipeline and show sort of what the baseline approach is here. So in the repository that you guys cloned at the beginning, we have a folder called examples bash, and I'll show it over in the VS Code window over here as well. So here's our repository. We have this examples folder, and then under the bash folder, you'll find each of the scripts that I was talking about. And in this case, we're going to go in and run bash, run pipeline.sh. And this is doing a very simple, sort of just what I showed, the naive bash implementation, and running it on just a single core CPU in serial. Terminal here, follow along as well. Okay. So I'm in the root of our repository. I'm going to cd into our examples bash directory, and I'm going to run bash, run pipeline.sh. And we'll see a bunch of output. Runs really fast because, of course, we're only moving some text around. But you can see that the pipeline is reporting what it's doing. So if I scroll back up here, we can see that it is, scrolling's a little slow on the display. This is the last step where it's doing the similarity computations between each pair of plays, but it's reporting each step. So before this, it was normalizing all of the text. It was writing the output of the top 100 files as it ranked and counted all of the appearances of each word. And that's great. So in our case, it finished in a number of seconds. But as I mentioned, this is a toy example designed to finish very quickly. And in your case, when you are running on real data, it may be a serious problem that you are just doing things one after the other and not really parallelizing. But we'll get to that. So the next thing that I wanted to show is that if we, here we are, down at the bottom here. So let's say that that worked great, and our first run was a huge success. But now we have some change in our data. So I'm going to take this command here, and I'm going to change one of Shakespeare's plays because I'm a decent writer. I think I can do it. So I'm just going to add one word change to the end of Hamlet.txt. And one can think that if we make just this tiny change to one of the data files, in a perfect world, it would be great to only have to rerun our data, if this is very expensive computation, for the data that changed. If none of the other plays have anything to do with Hamlet, then hopefully we wouldn't need to rerun them. Now, in our naive approach, of course, we don't have any handling for that. It's going to rerun the entire pipeline again, even though Hamlet was the only play that changed, and even then only changed by one line. So this is an illustration of, I think, the first problem that people encounter when they are writing their own pipelines in Bash, and it works. But now when we want to scale up, or suddenly, our paper got popular and people are asking how to use our code, or submitting pull requests and saying, it'd be nice if you improved it to do this and that. This is usually one of the first things that you run into. I'm going to move on, but do we have any questions so far, just on the sort of baseline approach for this example? Okay. As soon as I can find my mouse. Okay. So this script works, great. We're running it on the login node, which fine for this workshop, but in the real world, if we're running it on the login node, it's going to be limited to using one CPU. If we try to parallelize it across multiple CPUs, the YCRC automated, task reapers will come in and kill your task because it's running on the login node, and that's no good. So for a real workflow, we usually request dedicated resources. We go out and run a Slurm job that runs to a queue, a partition that has compute nodes on it, like day or development. We usually run in the background, so we'll submit the job, and we know it's going to take 5 or 6 hours, so we come back later, check on it, and we will get an email when the job finishes or fails. So the idea here is that I want to wrap this run all script in a Slurm job with SBatch directives, and this is a little better. It'll get us in the habit of running Slurm jobs and running our computation on compute nodes, but it still has this issue where there's no real parallelism. So let me show you what that looks like. Get back over here. Close that. So if I have, if I can do a side-by-side here, let's see how fancy we can get. Very nice. Okay, so on the left, we have the original script. And on the right, you can see that everything south of line 11 is exactly the same. So in this case, we've really just taken what we were just running on the login node, and we've added some Slurm directives on the top to tell the cluster that we want to submit a batch job that's named pipeline. It's on the development partition. We think it'll take 30 minutes. We're asking for 1 CPU and 1 GB of RAM. And when it finishes, it should email you at yale.edu. And that's great. So everyone probably knows how to do that already. And this already is a good improvement. It will probably still run faster on the CPUs that we have on the compute nodes compared to the one on the login node. But because we haven't actually changed our code to do anything. We haven't really split this out so that step 1 is a separate job from step 2, and maybe step 1 is 10 separate jobs, 1 for each play. We're not really benefiting from any of the parallelization here that we get from things like Slurm jobs. So that is exactly the point where I want to start talking about pipelining tools like Snakemake, which is the first one we'll touch on, because I can show you that we still don't have to do a lot of changes to our code to take advantage of a tool like that. So in Snakemake, first of all, what is Snakemake? So Snakemake is a tool. It's essentially based in Python, which means that when you are writing Snakemake files that define your pipeline, you are writing code that looks very similar to Python. And in many cases, it is Python code. So it's fairly easy to read. It may be familiar if you've used it before. And Snakemake has a few concepts that it uses to sort of ingest and run your pipeline. So in Snakemake, you define what are called rules. And each rule is essentially a step in our pipeline, one of the tasks that act as the nodes of our directed acyclic graphs, the things that act on data. Each of these rules has inputs that we define, it has outputs that we define, and then we define some commands, either using a script or calling some other script file that produce the output from the input. And when you have defined those things for each rule, Snakemake will essentially do the rest for you. It will build the DAG, it will run the tasks in the right order, it will compute what tasks need to happen first, it will determine what tasks can be run without needing to wait for anything, and which tasks need to wait for other tasks to finish first. And Snakemake also allows you to just run shell code like we've already completed here, or Python code or R code, or really anything that you need in your scripts to actually run those rules. So let's look at a little bit more detail. The key concepts, the things that actually make a Snakemake pipeline, you have something called the snake file. And in this case, that's the main file that defines our workflow. It's where we put all of the rules. It's where we put all of our configuration for the pipeline. Pull it up here. Looks like this, very similar to Python syntax for a lot of things. And I'll be going in much more detail here in a minute, but this is just sort of what the file looks like. And for our simple case, we just have one big snake file that contains all of our steps. Each of the rules that we define has an input, output, and a shell element in our case. And we can use wildcards, similar to like if you are, copying star.txt to copy all text files. We can use wildcards to create input lists from file name patterns. And I'll show you how that works as we want to define this for, say, all of the text files that have Shakespeare's plays in them. So in every snake file, we have a rule called all. This is sort of the very, the very generic starting point that Snakemake is looking for when it processes your file and starts to set up how your pipeline should run. So Snakemake, in essence, works backwards from the rule all target. So every pipeline needs a rule all, and its input is our final deliverable of the pipeline. So in our case, we know that the pipeline is finished running and has been successful when we have created this output /similarity matrix.csv file. In the snake file, this rule all is always the first rule, and Snakemake will use it to basically track backwards from all to determine what needs to run in what order. And nothing runs when you run Snakemake unless it's needed to produce this target. So we'll see an example of that, but that property at the bottom is what gives us the ability to rerun just one data file and rather than run our entire set of data again. Question?
In the rule all, can you put additional criteria of kind of checking if the file was produced and it's accurate or healthy or in the format that you expect, or does that go somewhere else?
Yeah, so the question is if we have some additional acceptance criteria where we don't care just that that matrix exists, but we care that it has some properties that tell us that it ran correctly. I would say that in our case, we want to keep rule all as simple as possible. It really only exists to give Snakemake somewhere to start. I would make a separate rule that is maybe like a verify or validation rule that performs that logic for you. But for our case, rule all is just the telling Snakemake where it should start when it wants to track how our rules interact and what their dependencies are.
So is each rule like a task, and so then each rule can run on a different node in parallel in theory for each sample.
Yes, so yeah, question is each rule a task? And does that mean that you can split out each rule and run over different data and run on a different node or run in different parallelization at the same time? The answer is yes. So each rule, when Snakemake processes your pipeline, it will be able to parallelize each rule into one run using a certain amount of input data. So I'm about to show that we will have kind of like a wildcard that says run this rule on all play files. And when Snakemake turns that into the real actions that are running on the clusters, it can submit a different job for each play file using the same rule.
And then also, say your play files are really, really, really big and it's taking a long time. So, or like you have a lot of reads or something, can you even split that even further? Like say you want to look at like the first X chunk of play one, or would you never, like you wanted to parallelize as much as you could and run it as fast as possible?
Yeah, so when we start asking things like how can I break this up further, and what's really the smallest unit of work that makes sense to do in a pipeline, that kind of gets back to the concept I was talking about called atomicity. So when we are designing our pipeline, we want to be asking that question of ourselves pretty frequently. Is it possible to break this piece of work up into a smaller individual task that we know fails or we know succeeds? In the genomic context, when you are working with, aligning a huge amount of reads to a large complex genome, it can kind of be tool specific. So like in that case, it depends what aligner you're using. Sometimes they can allow you to split reads up into different chunks and run chunks of reads over here and run chunks of reads over there. That's something that's very specific to the architecture of your problem. So I would say definitely keep it in mind and continue to ask yourself, is there somewhere that I can break this up to keep things independent and split them into more parts? But the specifics are usually up to the type of work that you're doing. All right, so here we have our first example of some actual Snakemake code. I have on the left our original bash script, and this is the sort of code that's doing the work when we get to the clean text step. So in our case, on the left, the bash code grabs the full input file. It then uses some Linux terminal built-ins. TR is like a translate, maps one set of characters to another. So in this case, it uses TR to map all uppercase letters to lowercase. It deletes all punctuation characters, and then it substitutes any space characters to new lines so that every word is on its own line. And then we output that to this clean.txt named for the same name of the play file. On Snakemake, we can see that this is very similar. In fact, we use virtually the same code in the Snakemake block when it calls shell as we did in the original bash code. So we don't really have to rewrite a ton of it. What we do create for Snakemake is we name the rule so that it's called clean text. We say that the input is going to be the data folder / play.txt. And here I've used these curly brackets around play so that we know that play is a wildcard. It means that this one rule can identify when it actually runs that there are 10 text files in this folder, and whatever the current one we're running on, we'll just refer to it as the variable play. The output is very similar. We say that this rule is going to produce output in the output folder, and then that same play variable .clean.txt. So when it is finished running, we use this in the shell code as well. Output is going to use the same output path that we give here, so that when we run this code, it's piping, just as we did on the left here. We pipe to output / play.clean.txt. On the right, this output will get completely replaced by what we've defined for the output here. And we have one nice little thing that Snakemake does for us is we can use this little temp feature that it has, where we know that this is just an intermediate file. we are going to be using it for downstream processes in the pipeline. But when the whole pipeline's done, we don't need all these files that we were using just for processing. So by wrapping this output in a temp, Snakemake allows us to just automatically delete it once we've confirmed that the pipeline is finished, which is a nice little thing that helps us keep our work as clean as possible.
When the pipeline finished successfully, the intermediate file will be deleted automatically.
Yes, so as soon as Snakemake is verified that the pipeline is finished, meaning the final rule all that we define has its output file, and all of the previous rules ran successfully, it will do a little cleanup step and it finds anything that's marked temporary and deletes it for us.
All of the examples in the snake file that you've given are the exact code that needs to be run.
Mm-hmm.
Is it acceptable to say like, oh, I have this single step that might be, 2,800, however many lines of code, to have that be a script that Snakemake calls, or does that break something?
Yeah, absolutely. So I think I have a couple examples later on, but essentially when you are using a block in Snakemake like shell, you can run basically anything that you would in your normal bash like terminal context. So if you had, say, in R, you're on the cluster and you had an R script that you wanted to run as the step, you could tell the shell command to be module load R and R script, my R script.R. If it was Python, you could say, module load mini conda and conda activate my environment and Python, my Python script. So I'm using the raw bash code here just to illustrate that no matter what your code is, it is still being interpreted as sort of native Linux bash script. But because it is doing that, you can also just import any code that you want or call out to any other code if you have the right interpreter or tool to run it.
Thank you.
Okay. So I'll go through the other steps. We also have count words. So in this case, we're just using a few terminal tools as we did before. We have, we're going to take the output from the last step, which is the clean.txt. We're going to sort it. We're going to count the unique words. We're going to sort those from the highest count to the lowest count. And then we're going to call that counts.txt in the output. And Snakemake, this is the first time that we have a dependency. So Snakemake knows that count words needs to wait for clean text to run because it's looking at this, it's looking for the similarity between the output and the input paths that we give it. So in the previous step, clean text, we said our output is output/play.clean.txt. And in count words, we say that the input is output/play.clean.txt. So the input path for this step matches the output path for the last step. And Snakemake identifies that, and that's what it uses to build the dependencies in the graph. So it knows that count words depends on clean text. So it's keeping a record of the clean text step needs to run before the count words step can run. Next step is just the top 100 words. Pretty simple. We just use head to grab the top 100 of that sorted ranked count list. I kept this in just to illustrate again that on the left, we actually had to manually remove some of those intermediate files. Snakemake does that for us, as we discussed, because we wrapped them in temp. In our final output, in this case, I just kept the top 100 here. In this case, I wrote originally that this is the final deliverable. I later changed that to be it's a CSV now, but the idea is that if I don't put temp here, this might be useful to be a spot check. So if my pipeline runs and I want to say, okay, well, I'm not really going to go in and read all of the cleaned count files or the full ranked list of counts, but I might want to go in after it runs for a few of them and just check the top 100 and see if that makes sense. I can easily just keep that there without the little temp trick that we were using before, so that this stays after the pipeline runs and I can go in and check that. And if I need to delete it on my own, I can.
Does this seem similar to using signals and slots in C++?
It is a very similar idea, yes.
Okay. Are there any major differences other than the language?
So between C++ and Snakemake, I would say the largest difference is typing. So if in C++ you're used to defining slots and using signals between them that have certain types, Snakemake, because it's based in Python, doesn't really care that much about specific data types. It has, I believe that its base data type is a path. So most of what it's expecting to find is, yes, a string, but the string represents a path here. So if you have, say, types of data that are more better represented by a data type, like maybe you want to pass raw images around rather than actually go to the disk and read and write file paths, then Snakemake is a little less designed for that kind of use case. But that's one of the things that we'll talk about in contrast with Nextflow, is that Nextflow is a much more abstracted type of pipelining ecosystem, so that it does add a little more complexity, but also allows you to sort of define in a more custom way what you want your data to look like as it goes through the pipeline.
Okay, thank you. That's really helpful.
Rob.
Yeah, Sam, can you talk a little bit more about how the matching happens between output and input? You know, in the example here, they're so similar. You just sort of, oh, I get it. But play is just a placeholder here. Like I could have named the second instance in my second rule. I could have used a different word for play, and it should still work.
Sure.
So is it evaluating all those and then matching, or is it matching the abstract rules?
So when we actually run the pipeline, we say, you know, Snakemake my pipeline snakefile. One of the first things that it is doing is it's actually going to go in and review all of these variables and create a filled-in version of everything. So rather than all of the rules having a play variable for the input, play variable for the output, it's going to create, say, 10 clean words steps. It'll say, you know, we have 10 clean text steps, and their inputs are Hamlet.txt and Othello.txt and Twelfth Night.txt. And what it does then is it goes through those sort of filled in versions, and it uses those to connect where they're similar. So the existence of the variables is really just for us to prevent us from having to write, you know, 100 different rules for each type of input file and output file that we have. But when Snakemake does the processing, it's actually going in and replacing those to create the real list of, you know, all 10,000 files or however many you're processing, so that because it's, you know, a computer, it can do it really fast. It's no problem for it to enumerate everything manually, and that's how it does the actual matches.
Can we check those roulette lists before doing like a run, like a dry run of it?
Yes.
Like this is very good, like to check like if everything is matching.
Exactly. Yes. So there's a few tools that we can use that I will get to in a few slides, but I thought it was the next slide, but it's a couple more. So you can run a dry run to essentially see how many of each step it thinks it will need to run, and you can also trace what the graph looks like and have it draw an image of the graph for you that you can inspect and see that it makes sense that the steps are operating in the order that you expect and the data is moving the right way and so on. Okay. Finally, I won't belabor going through every line of these, but it's very similar for the compare plays as well. In this case, I just want to point out that we're using two wildcards here, because in this case, we have two plays that we want to pair up in each of these rules. So when we run compare plays, we have play one and play two. And so we use two variables in the inputs. We can use them both in the outputs, and we can also use them in the outputs in the shell line, which actually is long enough that it didn't make it all the way. I couldn't fit it all on the slide, but I'll throw find it right here in snake file, just to illustrate really quickly. Back up. A little laggy. Whoa. There we go. Okay, so it looks kind of like this, where we can, we said on our inputs that, okay, we'll call this variable top one, that's our first input, and it's output play one, and top two is output play two. And so when we're actually writing our shell script, we can say input, getting the namespace of the inputs, dot top one, the name of the variable that we defined, and that's how it sort of injects those paths in when we're actually running the code. So it works very similarly to a lot of other scripting languages that allow sort of variable and string interpolation at runtime. So things like Perl can do that, Python does that. It's a pretty common pattern. Okay. All right, let's get back over here. Okay, now finally, the combined results step. This is where we have just a little change. This maybe the most different from the original bash script. So originally, when we were running the bash script, if you remember, we had this nested for loop that allows us to index over each pair of plays and create all 45 plays between each of the 10 plays, each 45 pairs of 10 plays. Now, in our case, because Snakemake is going to process our entire file and define the graph at once, we need to tell it what those pairs will be so that we can reference them later. So you'll notice that, and I won't try to scroll because it's laggy, but at the very top of the Snakemake file, before I start defining all of my rules, I have some code here that says, let's generate all unique pairs of the plays. So I'm just using some Python. It's another nice thing of Snakemake being Python under the hood, is that I can just use the itertools package to bring combinations in and do some combinatoric stuff really easily. So that I'm just creating all possible pairs of plays, and then I can just say that all the first pair plays are just the 0th in those pairs, and all the second pair plays in those pairs is the first. And when we have that, we can then just reference that in our actual scripts. So now that we've created this pairs variable, when we actually write code for Snakemake, we can just reference it. Like here, we have loops going through that allow us to go over each pair of plays. So we get the index, we get the first name of the play, and then we loop again over the second name of the play for the remaining plays to create the final pair of plays. So I did it in one way here, just to sort of show the one-to-one translation from bash. And then in the Snakemake file, I did it slightly easier with the itertools library in Python, because what's the point of using Python if you're not using all the awesome built-in stuff? Okay. All right, I get through here. Let's talk about how we actually run this. So we have our Snake file set up. We've translated all of our bash into Snakemake, for the most part, reusing the bash wholesale. And now let's actually try running some Snakemake and see what happens. So if I want to run Snakemake, the first thing I usually do is I will run with -n, which is what gives us a dry run. So if I run Snakemake -n, say I'm going to go here, I'm going to go into, should still be in here, yep. So I'm going to say Snakemake, oops, I'm going to go out into Snakemake. So now I have my snake file here. Oops, take a look at it, and yep, that's the file I expect. So if I, on the clusters, I will first module load Snakemake. There we go. And then I'll just Snakemake -n. It will go through. And essentially what you see is that it has computed all of the jobs that need to run by looking at all of the outputs that I've defined in my pipeline. So any output that's missing, it's going to work backwards and determine what tasks, which are the rules we define, need to run, and how many instances of them need to run to produce all the output that I've asked for. So if we scroll up of this, we'll see that it's actually doing this huge verbose enumeration of every job and why certain jobs need to run, and what files specifically are missing and what parameters they have. Try to avoid scrolling too much because it lags the monitor. But you can see here, this is the last job where it's the big combination job, and it's saying, well, if we want to do that, based on how you've defined the pipeline, you first need the outputs for all these other files. And here it's asking for, if you want to compare King Lear and Othello, you need to do the jobs for all the Othello plays and all the King Lear jobs first, and so on. So when we are accepting of what Snakemake has planned. We just run it without the dash n to run the pipeline for real, actually do all the processing. One more tool that I wanted to show off is that Snakemake also has a little nice feature that allows us to generate the graph that I mentioned. So we can generate the DAG of our pipeline and then render it in, so essentially this is 2 steps where first we produce a sort of a text file that is renderable with the Linux tool dot for SVG and vector graphics. Then we render it to a PNG file. And when we run that, it creates this gigantic, humongous 45 long comparison block. But I will zoom in here. So you can see that it has rendered us the actual steps that it's going to run. And as I mentioned, it fills in where our variables were with the individual play names for each of those variables at each step. So where we defined that clean text exists for a play.text, it now has filled in that the variable play in this run is Macbeth, and on this run, it's Othello. And when we get down to the comparison step, it's created for our variable play 1 and play 2 that we used. For instance, this one is Julius Caesar versus Merchants of Venice. This one's Macbeth versus Othello, and so on. And then at the end, they all come down to the combined results. And finally, the all rule that we define as the sort of meta rule that tells us when we're done. So I'm trying to make a case here that if you have a script pipeline, or a series of scripts, or a bunch of bash code that runs your analysis for you, you should consider using a tool like Snakemake because you get a lot of stuff for free. So you don't have to write that much more code. You get DAG visualization, you get automatic dependency resolution. It will only rerun steps whose inputs have changed. And you can very easily rerun things. You can run in parallel execution with just a simple flag to pick how many cores you want to run on. And like we just saw, it has a dry run mode. So I wanted to show one thing here. How are we doing on time? I wanted to show an example where, remember we had that test before where we had just changed one of the plays, where I had done something like echo lean to Hamlet. And when we were just running this on the bash version, we didn't really have any handling for this. It just needed to rerun everything automatically. So I'm going to run, actually I have to run this first. So let me run Snakemake, and it's going to do all the processing. Like I said, it's, just doing some text processing, so it shouldn't take very long. Of course, it adds a little bit of overhead. So whereas it might have taken 20 seconds to run in Snakemake, if we didn't have the overhead, it might take 15. But at the very end, you could say it ran 77 of 77 steps that it counted in the original dry run, and everything's good. So now let's say I go ahead and add some new text to Hamlet. So if I run again and ask it for a dry run, it will tell me that it actually only needs to run 14 steps now. In this case, it only needs to run 1 play's worth of clean text and count words and top words. And it needs to run 9 comparisons because Hamlet changed. So we need to redo each of the comparisons that Hamlet was a part of. So rather than our pipeline needing to redo 77 steps from scratch, Snakemake is smart enough that it knows that the input file has changed for Hamlet. So we only really need to rerun 14 steps that Hamlet was a part of. And we didn't write any code to do that. We just moved things over into Snakemake, and now we're running in Snakemake instead of bash itself. So that's just one of the things that when I say you get stuff for free, that's one of the things I'm talking about. Okay, however, we are not done yet. We can still make this better, and that's because I haven't really mentioned running on the cluster at all yet. For the most part, what I've done here is really just a simulation of what might be happening on the login node or on a local computer, and we're not really taking advantage of the parallelization that we can run on multiple compute nodes on clusters. So when we run Snakemake, we have a bunch of different options available to us. One of the things that we can do is we can run with this executor option and tell it to use Slurm as the executor. And when it does that, it will begin to submit each of the rules rather than running them locally on the login node on the local CPU. It will submit each of them as a Slurm job. And we can give it some additional parameters to tell it how many resources to use by default. And even within each of the rules, if we have specifics, we can tell certain rules to use certain Slurm resources or certain Slurm partitions or whatever customization we may need to make sure that that job runs as we expect on the cluster. And there's a note here, if you are running this in a Python environment, there's like a little extra Python package you have to install to get the Slurm plugin to work with Snakemake. So let me show you an example of that. Now, I said that we can, it's so easy, we can just add one plugin command to set Slurm as the executor and all our jobs will now run on the cluster nodes. Well, what if we don't really need that to happen? And it's usually very common that while we do have a lot of heavy processing steps, maybe, again, in the life sciences context, the, running the aligner to map all your reads or, maybe doing like variant calls or something, stuff that really takes a long time. We want that to happen in the cluster nodes. We want that to happen on the compute nodes where it's going to go as fast as possible on compute that is optimized for it. But not every rule needs that to happen. The lightweight stuff, like combining the results back together, maybe like trimming adapter reads or doing some pre-processing, doesn't need all the overhead of waiting in the queue for the Slurm node to be ready. So it would be nice if we could just run that on the local node, on the login node or on the local machine or some head node that we're using to orchestrate our jobs. Snakemake thought of that, and it has this feature called local rules, where in the snake file, you can just add this little line that says local rules are all, because that's a simple check. It doesn't need to run on a Slurm node. And let's say combine results. That's just combining some text files together. So that really shouldn't take that long. We'll make sure that that doesn't run on a Slurm job. And then everything else that is not defined in local rules gets submitted to Slurm via the executor Slurm argument. Further, if we want to add custom resources for each rule, we have options there as well. So whereas so far we've seen in our rules that we put in the snake file, we have input for defining the input paths we expect, output for our outputs will be named, shell for the actual commands that are running. We also have options to add things like threads to essentially pass to Slurm the CPUs per task option. We have resources to give additional things like the memory used in the job, the runtime for how long in minutes we expect that job to finish. And this allows us to tell Slurm when we're submitting jobs for this rule, how much resources to use, just as we did previously when we added the run pipeline Slurm, when we have these SBatch directives that we use when we're submitting a batch job with SBatch, as you may be familiar. So essentially, we are able to automate the creation and submission of batch jobs just by defining it in the same place that we're doing in the pipeline already.
Can you put anything that would go in the SBatch header in that resources? Like if you have to submit some jobs to GPU queues and some to CPU, you can specify that? Yeah,
absolutely. So it's, I need to look up in the documentation for this pipeline what the syntax is, but under resources, you would just add like GRES equals whatever the GRES string you use for like GPU requests is. And everything that's supported in Slurm should also have a correspondence in the Snakemake syntax. Okay. So we had someone had asked before, well, what happens if I have this 1,000-line script that is one of my steps to my pipeline? Can I just call that somehow? And I mentioned that yes, you can definitely do that. You can simply do it through the shell block as we used before for shell script and just say like Python myscript.py. You can also use a different directive called script, where you just pass it the script, and then you can use in your Python scripts or your R scripts a special object that makes your scripts aware that they're being run in Snakemake. So if I want to write my script, in this case, let's say I had some plot heat map and I have some data CSV, my script can then go back to Snakemake and reference the Snakemake file of what should the input file be. So I can then define my workflow so that all of the inputs and outputs are defined in the Snake file, and my scripts that actually take those inputs and run processing on them and write to the outputs can use what's written in the Snake file to get what it needs to write the correct file paths. So this is in contrast to if I had, say, if this was just a standalone Python file, I would either need some code that, in our Shakespeare example, looks up all the plays and gets the right play for the instance that we're on and runs the processing. Or I could just reference the Snake file, and then I know that I have this one script that, regardless of what play I'm on, what data I'm actually running on in this instance, will get the right input and output paths and any other variables that we might define in the Snakemake file.
I know that some of the partitions have number of like job submission per hour limits. Is there a way to tell Snakemake like these 3 steps could go together in one Slurm job?
Yes, so the question is, we have on our clusters, we have limits for how many jobs you can submit in an hour. And that's sort of to prevent people from overloading the scheduler. In Snakemake, there are directives similarly to how we had the like the resources and threads that can limit jobs per hour. So it's also documented in the same sort of syntax for the Slurm plugin. And you can also use a more global configuration file. So like, let's say, and I'll touch on this when we get into Nextflow, but let's say we have some pipeline we have to run for like 10,000 samples. We can add a global configuration that says, at any point during this pipeline run, the most jobs you'll ever be able to run at one time is like 50 concurrent jobs. So it will then take that, and it will, when it's managing what jobs are running and what jobs need to be submitted, it will try to ensure that only 50 are running at a time. And you can tune that, depending on how what partition you're working on. If you're using, priority queue or private partitions or whatever, you can tweak that however it may need to be.
So if we don't set that, what will happen? The Snakemake will fail or just wait for the resources.
So by default, it will submit up to whatever the limit is and then wait.
Yeah, so if in 1 hour, so we reach the upper limit, so the Snakemake job will just wait for the resources?
Yes.
Okay.
So if you have, for instance, jobs that can complete more jobs with fewer resources, it may make sense to specify that in the file so that it knows it can submit more jobs with less resources and not wait as long. So it can be useful to set the defaults as well to something a little lower so that it doesn't get stuck waiting for maximum resources. Okay, very similar. So how we had just mentioned, you can reference Snakemake definitions in Python files. You can do the same thing in R as well. So the syntax is a little different. You use this magical Snakemake variable appears, and then you can index its input variable and then get the actual index of that entry. Same thing with output. So that you can do similar patterns for Python and R. These are, I believe Python and R are special in that Snakemake has some additional code under the hood to do these kind of substitutions and interpolations. For anything that it is not explicitly supported in that way, you can still use the shell command to call your MATLAB scripts, Julia scripts, C++, whatever it may be. This is just a little extra nicety that they threw in because it's so common in the Python and R patterns. One last slightly more advanced topic, but very useful one, is containers and containerization in Snakemake. So I touched a little bit upon how important reproducibility can be, especially when you have complex code artifacts and a complex pipeline. One of the best tools that has appeared in recent years for reproducibility for us in bioinformatics and data analysis has been containerization and virtualization. So if you're not familiar, there's a tool, the most popular one is called Docker, that allows you to create what are essentially very lightweight virtual machines. So a container essentially wraps up all of the code and tools that you need, essentially creating its own virtual computer, a Linux computer that has just what you need installed to complete the code that you want to process on it. Now, this means that if you can define what makes your container run, you can hand that to someone else and they can build the same container to run your code in. This is different than you running your code on your computer directly and then them taking the code and trying to run it on their computer directly. Those two computers may be set up completely differently. They may have different versions of software, of the operating system. If instead we run the pipeline code inside a container that we control the versions of, control the operating system of, we know that both people will always be running on the same exact underlying sort of architecture. We have a much better shot at that being perfectly reproducible. And so people that design pipelining software have tried to build this as an advantage of something that you can use in their software as well. So for each rule in Snakemake, for example, you can also define a container that it should run in. And containers can be defined by, say, a Docker Hub URL, like this one here, which is for the BWA aligner. And when that means that when this runs, it will, rather than just run on the same computer that Snakemake is running on, it will first use Docker, or on the clusters, we use Apptainer to start this container. And then it will pass that shell command and all the data. It mounts the data directory so that it has access to the input and output files it needs, and it will run that within the container. So that means that you have a fairly easy way to, with just a little bit more work, to find a container or build a container for your project. You get a lot more reproducibility, and it's a lot easier to pick up your code and run it somewhere else, or have a colleague get it up and running. Question?
I think you just answered it, but I just to make sure that I'm understanding. So like you have in your lab, like a lot of people are working on the same type of assay, and say like it's very difficult to set up your environments and stuff, and everyone's doing this separately on their HPC account. Instead, one person can make a container, an Apptainer, and port that to someone else who could then use it to run the same.
Yeah, it would help a lot if you have multiple people running. So you have a lot of people in a lab. They know that you need to set up a Python environment and a certain maybe set of R packages to run the code that we need. But who's to say that everyone, when they did that setup, downloaded the exact same version of every Python package, the exact same version of every R package? By setting up a container for this pipeline, essentially all of that is pre-installed and ready to go. All they need to do to, say, run your pipeline on new data is run the container, or using Snakemake, define the container, and it will automatically run that code inside the container for you. So it's a really nice way to kind of remove a whole class of issues that you run into, where two people setting things up with very small differences in the way that they do things, or the order in which they do things, can result in two different environments. And when we're trying to reproduce science, we want things to be as identical as possible, and to make it as easy as possible to create the same environment to run our science in. So containers are a great way to do that.
So when we use Apptainer, at the shell part, we don't have to write Apptainer run or something like that.
That's right. So Snakemake handles actually running Apptainer and starting the container for you. So once that container is started, it's just running the shell command that you tell it inside the container itself. You don't actually have to run Apptainer. It would be like Apptainer exec whatever the command is to start your container, and it handles all that for you.
Do we have to tell it like, hey, we want to use Apptainer, but here's the Docker path, or does it know?
Yeah, so do we need to do anything special to use like a Docker, an image that was built for Docker on Apptainer and the clusters? No, we don't actually. Apptainer is built to be fully interoperable with Docker. So even Docker Hub images, you can just give it the URL and it will It does need to build its own version of the image, but it can do so automatically.
Okay.
Yeah. And the local image format that Aptainer uses is called SIF. So if you have a .sif file that you've built yourself, you can also just point it directly to that image, and it will start a container using it. Right. So yes, so how we do that is we will just use this SDM flag, which stands for Software Deployment Method. And we say SDM Aptainer, and now Snakemake knows that I'm looking for container directives in each of the rules. I will first add a step that goes and pulls all of them, caches them on the drive, and then each rule that has that defined will run in its own isolated container. Now, in our example, obviously, I didn't add any containerization examples for the Shakespeare stuff because it was already getting a little overwrought for the weight of the example. But it's something I highly recommend you look into as applicable for your work. Okay, so last thing that we'll do, I think, before break, is I just want everyone to, if you haven't yet, go into the Snakemake examples, module load Snakemake if you're on the clusters, run the dry run, familiarize yourself with that kind of output, and then go ahead and execute and actually watch it run through and update as it gets through each of the tasks. The output, let's get the output too. The output file should exist. It'll be output/similarity matrix.csv once you're finished running. And then just like you saw me demo on the board, you can also simulate a data change by adding a word to one of the files and then rerun the Snakemake dry run. It should show that, if you changed one play, only 14 instead of 77 jobs need to rerun.
One more question on the Aptainer thing. Say you need a container for like one specific step. Can you still specify Aptainer as the SDM? And then other steps will just use like a Conda environment or something else?
Right. So if you don't specify a container under that rule, that step, it will just fall back to running that step on whatever the Snakemake was started on, basically. So you don't need to define a container for every step, but if maybe you have some steps that it's useful for and some that it doesn't really matter. So. All right, I'm gonna go back over to the board here. So over here, I had just run Snakemake-n for dry run. And this is after I had added one new line to Hamlet. And it's telling me I only need to run 14 jobs. That's great. And then if I say want to look at the output, it's an output similarity matrix. There we go. So this is what we expect. It's a CSV where the columns are the name of the first play, name of the second play for each of these pairs, and then the similarity score that was computed. So if we wanted to send that out, that's the full CSV. It's like no, it's bytes. Kilobyte. So looks like it ran okay. All right, I want to show one more thing. And we'll go take a break before we start talking about Nextflow. So I had spoken a little bit about how Snakemake runs on Slurm, how it can be very intelligent about sending each specific rule as its own Slurm job. I want to show you what that actually looks like when we run here. So I have, let me find it, Snakemake Slurm. So I have just created this file here. So in this case, I am going to run the full Snakemake call inside a Slurm job. So I'm saying module load Snakemake. I have the sbatch commands up here. And up here, I've only defined what I think the resources that we'll need for running like the head Snakemake node. So this isn't the resources that I think the tasks within my pipeline will need. This is just the very lightweight stuff that Snakemake needs to do its overhead. It's sort of managing and launching jobs. So within this, I will actually write Snakemake. I'll say, use parallelism of 2, use the Slurm executor. Latency weight 30 was a little tip I'll mention at the end. Default resources. In my case, I want to run on admin tests because I'm doing a workshop. A gig of RAM, 1 CPU per task, and say 5 minutes per task. Latency weight, I think is a useful thing to note. There are cases in when you're running on our cluster that because our file system is what's called a networked file system, it's network attached. If you're saving files to say your project directory or Scratch directory, there can be times depending on the usage where one process writes a file to the network storage, project, Scratch, etc., and another file reads it, and it may not exist yet until maybe 4 or 5 seconds later. This is usually you don't notice this because by the time you go over and try to read a file, it's updated. But in automated situations like this, Snakemake might fail because it's told that the task finished, but it can't see the output file yet. So I add this little latency wait argument to give it at most wait 30 seconds before you actually report that the file is missing. It's just a thing to keep in mind because I ran into that one day and had to look into how it worked, and that was the solution. So, all right, so let me run this and I'll show you what it actually looks like when we are running on Slurm. So where am I? Oh, great. So let's run Snakemake Slurm. All right, so we've submitted a batch job, and let me see if it's running. Yep. So let me tail my output file. The output file. And let it start up. All right, so it has noted that it needs to run 14 jobs. And now each time, rather than running locally for the jobs that actually contain work, it's saying, okay, well, job 8 has been submitted as its own Slurm job, in this case with this Slurm job ID. And its individual log file is here. So as I'm running this, maybe this is like a pipeline that takes all day to run. I can go in and check this log file and see that, okay, well, it's just run this file. And if I want to go and see the individual log for, maybe that's, that looks like it's the Hamlet clean text step, I can go and read that file specifically. So this is a good pattern to use for larger, longer pipelines. The downside is that there's a lot more overhead to actually submit individual Slurm jobs than to just run things locally. That's another illustration of why, if you have something that runs really fast, doesn't really require a compute node, you can just do local rules. So it's just going to keep doing this for the next few minutes, so I'll let it run while we take a break. But yeah, that's for the more or less, that is our quick overview of Snakemake. When we come back from break, we are going to start talking about Nextflow. I'm not going to go into as much detail on the one-to-one translation of our original example into Nextflow. I'm going to be talking a little bit about how its architecture compares to Snakemake, and I'll be talking about how most people used Nextflow, which today, maybe one day, we can hope. Yes, so most people use Nextflow with pre-existing pipelines. So like there's in life sciences, at least, there's a really big community of people that are publishing pipelines that are like all the best practices of how to do things of certain types of analysis. So I'll be talking a little bit about how that works and how to find pipelines and that kind of thing. But for now, let's take a 10-minute break, use the bathroom, get some water, and we'll come back in 10. All right, so we had just finished up talking about Snakemake, which is the first pipelining tool that I'm covering today. The second one is called Nextflow. They are similar and different. Nextflow is very, very similar in what it's trying to do, where it's trying to give you a system to manage and sort of codify data pipelines. And it's a little bit different from Snakemake. So Snakemake was based in Python. Nextflow is based in something called Groovy, which is kind of like a Java YAML kind of combination, where Snakemake used mostly files and paths and rules to define our tasks and the data that we're operating on. Nextflow has the concepts of processes and channels, slightly more abstract. Also has built-in container support with Docker and Aptainer. And its programming model is what they call data flow, as opposed to a more scripting-based model used in Snakemake. So if it sounds like Nextflow is a little more abstract or complicated, that's probably true. It definitely is. That is and is not a bad thing. Whereas Snakemake is, I think, the best place to start if you have a pipeline that you want to get automated and have some nice management around. Snakemake's a great place to start. Nextflow is a lot more complex in that it allows you to define many more custom things to do in your pipeline. So if you need to do something like, I don't know, process images in your pipeline and have some, toll gate checks for whether your pipeline is working based on the ways that the images are being processed and what the results are, that could be really hard to do in Snakemake, and you might have to do some custom scripting and kind of work outside of Snakemake a little to make it happen. But Nextflow can probably just handle that for you if you can figure out how to define the channels in the right way to get the data flow working. So the key concepts here are processes, which are what we called a rule in Snakemake. So this is what defines a task. You have your inputs, your outputs, the scripts that you use to go from inputs to outputs. Channels are now, again, a little more abstract. They are at the edges of our DAG, the things that connect processes. Data flows through channels to go between processes. And operators are the things, the actions that transform and combine channels. So in Snakemake, everything that we used for input and output was basically a file path or a wildcard to a collection of file paths. So in our Shakespeare example, we had, play.txt would get all 10 of the plays. In Nextflow, a channel can work with file paths, and we can also use wildcards to say this is a channel that, finds all play.txt files, and that's our data input. But channels are also more abstract because they can be used to define many other ways of getting data into your pipeline. Things like streaming from an instrument or from the internet. You could define a channel that searches the file system and gets all the files that match a certain hash or something. So it is trying to give you many more tools with which you can define your pipeline, and it necessarily makes that a little bit more complex. Side by side, I think that the biggest difference is really the language and syntax. It's, at least to me, speaking as opinion, a lot easier to read a Snakemake file than it is to read a Nextflow file. I just think that the Python syntax and white space separation is a lot more readable than the groovy Java-based syntax. And the learning curve is definitely a little higher. As I mentioned, it's a little bit more abstracted, and that's because it wants to be able to do everything. And you can certainly do many more things within Nextflow without having to reach for something custom than you can in Snakemake. And one of the biggest differences, one of the things that Nextflow is really known for in data pipelines is that a lot of communities of practice have adopted Nextflow as their language of choice for publishing like public pipelines that people can use. So a lot of influential papers began to publish their code in Nextflow pipelines. A community sprung up called NF Core for life sciences and bioinformatics to provide high quality best practices built-in pipelines for a lot of different types of workflows. So I think the bottom line is that Snakemake is definitely more intuitive. And if I were, trying to convert a pipeline tomorrow, I would probably reach for Snakemake first. But Nextflow has many more features for more complex workflows. So if I was tomorrow starting a new development of a suite of tools that was going to, build pipelines that handle all of the genomic sequencing that we do at Yale, I would probably go with Nextflow because it's a big complex project, and I'm sure it'll handle the speed bump better. But let's go side by side. So just as before, where we were looking at our original bash script compared to Snakemake, now let's look at Snakemake versus how the same thing is defined in Nextflow. So far, things aren't looking too different. We have a process instead of a rule, where now we have this same block that defines some inputs, some outputs, and a script. So in the inputs, on Snakemake's side, it knew that, it's kind of by default, it's implied that what we're passing as input is going to be a path to a file. On Nextflow's side, an input can be many things and not just a path to a file. So we have to pass a type. In this case, the type is path, and we call it play. Now, the first thing that you're going to notice is, well, we haven't actually given it a file path yet. So how do we know what play actually becomes when we run this? In Nextflow, we define everything that fills into the process blocks at the very end of the file in what's called the workflow block, which I'll show you as we work through it. But basically, we define everything kind of as a variable in our processes, and then we fill it in at the end of once we've written all of our processes down. So in the output, on the left, we had, we're going to make this temporary, but basically we just have a little wildcard variable to say whatever the play is .clean.text for Snakemake. On the Nextflow side, we define, again, with a type. We're going to use a tuple, meaning a pair or more values. In this case, we want the play.base name. So we're now getting an attribute of the type object path, which has a base name. So all paths in Nextflow have a base name and have, like parent directories and, full path, unqualified path. So this is now much more like an object like you'd be familiar with in R or Python, where we can get attributes of the object. And we use that same base name of the play to do the same clean.text. In this case, we say, this is a value, again, asking for types, and this is a path. The script is actually maybe the most straightforward translation. Just as before, we had the input path. Here, we are using the name of our path input. So we just pass that as play. And then we do the same thing here as we did in the outputs, play.base name, just to get the pre-extension part of the file name, .clean.text. We had our own extension on that. So where does this play path thing come from? At the end of the Nextflow file, after we've defined our channels, after we've defined our processes, we do two things. First, we will create what's called a channel to collect all of the data files that we are going to use. And we will then use a workflow to define how those files flow from one step to the other and what we call the inputs at each of those steps and outputs. So in this case, I've first created what's called plays_ch, plays channel. And I said that let's make a channel from path. And here is where I put the path with the wildcard of all the text files in data. So when we did this in Snakemake, we did this directly, where I said data file. So we have the data folder, and then anything .text I will call play. In Nextflow, we just said, okay, well, there will be something coming later. We will input an argument to this function, essentially, of play, but we don't actually define it until we set up what the channel will be. All of the files called .text in the data directory. And when we actually set up our workflow, we say, okay, we want clean text, and clean text is looking for an input. So we will give it this channel that we made, plays channel. Within clean text, that is what becomes play. So the output is essentially the variable I assign this to. And I then take this cleaned output, use that as the input for the next step. Count words is given the input of cleaned. Its output is called counted. Top words is given the input of counted, and its output is going to be called top 100, and so on. So that where Snakemake kind of allowed us to just define the all rule and what it depended on, and then what those rules depended on, and those rules and so forth, and it kind of calculated all that for us. Because of Nextflow's like abstractions, it cannot just do that automatically. It requires us to add this workflow of how the rules are chained together. That affordance that Snakemake gives by just assuming everything is a path allows it to do some things like kind of automatically, like just connect that this path is this path, and the two of them are dependent on each other. So this task has to come before that task. In Nextflow, because we can't guarantee the type of the channels that we are sending into our workflow ahead of time, we have to add this definition of what order things are expected to be done in. So you can think of a channel as more or less a stream of data flowing between processes. It's the edge on the graph and the DAG. And Nextflow, much like Snakemake, will be smart and automatically parallelize. If you have 10 files in the channel, it will automatically generate 10 concurrent tasks and run them at the same time. So in Snakemake, the way that this worked was we had, when it processed our wildcards, it knew that we had a clean text task for Hamlet and one for Othello and one for Twelfth Night. In Nextflow's case, it's doing a similar thing, but it's just enumerating all of these when we actually, like it's saying we have one clean text and 10 inputs, as opposed to 10 clean text, each with one inputs. It's maybe slightly semantic, but it's the sort of the reason that Nextflow requires you to do this more explicitly. Okay, I'm now going to show. Let's take a quick look over on the side screen. I'm going to show off the what's called the main.nf file. So as before, we had the snake file was the name of like our main altogether workflow script. In Nextflow land, it's called main.nf, and I'm going to run it over here. And you can follow along if you like, but I'll show you how it works. Okay, so first, let's just take a look. Main.nf looks like this, and hopefully the scrolling seems to not lag when I use the arrow key, so I'll just do that. So when we scroll through, we started here, so we have the process clean text, and I've separated just as before that these all kind of go in the same order as I expect. And when we are, let me do one. We do one side by side here. So in top words, I had called out before that we didn't use the temporary when we were doing Snakemake. So like if I'm in, find back to the snake file. So when we were in Snakemake, and we did the top 100 words step, I called out and I said, okay, well, notice that I don't have the temp around this anymore. This could be too helpful. And that's because I wanted to actually see those files at the end of the pipeline and maybe use it as a spot check or something. In the same way in Nextflow, we actually need to explicitly say, okay, I want to copy these outputs. Yes. So we explicitly say in Nextflow, I'm going to publish these outputs and I'm going to copy them, meaning wherever they are in the working path while it's actually running the pipeline, don't just move them, make a copy into the output folder that I'm calling publish there. So Nextflow kind of decides by default that anything that is not published as output is treated as temporary. And I'll show in a minute where that all lives. But the idea is that Nextflow is doing everything in its own special work directory, and it treats everything as temporary unless you tell it not to. So it considers everything that is intermediate files, all the images and tools you might have to download to run your pipeline. All of that is in like a special directory called work. And if Nextflow feels like it needs to clean up or it's told to clean up, it'll just delete everything in the work directory. So anything that you want to keep needs to specifically be flagged as output and be told to either move or copy it to that directory. So there's the same thing that we were doing in Snakemake to keep a copy of the top 100 files to look at later. In this case, we have to be more explicit about it. Okay, so let me pull this terminal back up. So we run back through the rest of these steps, just as before. This is the part where we're wiring up the workflow. So I'm saying, okay, we have this plays.ch channel where we define all of our, where we define what our wildcard is for the input files. And then each of those go through one at a time to the next chain in the path. Now this part before where we had done these loops to make the actual pairs of plays one after the other, 45 pairs from 10 plays. In our case, we've created this top 100 from running the top words list. And now we're using some built-ins in the Groovy language spec that allow us to do almost like a MapReduce kind of flow, where we want to we take what is in top 100, and now we're renaming it so that what is originally 4 values is now a name, the top count, the second name, the top count, and then mapping these over into a tuple. If it seems like we're doing things that are more complex for really no reason, it's because Nextflow is a little bit more opinionated about how you need to define things. In Snakemake, we kind of were on what programmers would call the happy path. The way that we want to define our pipeline is exactly the way that Snakemake is built to be used. In Nextflow's world, it does not try to force you down any one way of developing and defining your pipeline. And that means that if we want to do anything that's more complex than, say, running a process and adding it to a value, we have to play by Nextflow's rules. So essentially, we have to change our language a little bit to be able to create the set of pairs that we want Nextflow to use to pass over to the compare plays. So once we actually have that, it works just as it does before, where we tell it what the input is, we tell it what we name the output, and then the final step where we combine our results is just a .collect on similarities. And this .collect comes from like the whole MapReduce world and Spark, and the idea of kind of delayed or lazy processing, where I can define everything in the programming, but until I actually do something to it, until I try to compute the sum or collect the output, it's all just a graph. It hasn't actually done anything yet. It's on the paper and it hasn't actually run. So when we actually want to run everything, we do this .collect, and that tells Nextflow that when we get here, okay, we actually want to go and run all the dependencies and create everything that's needed to get that output. Okay, so you're beginning to see a little bit. Yeah, go ahead, Rob.
Yeah. I think I'm following, but cleaned and counted in top 100, those are channels that in this case each have 10 elements in them. Is that true?
Yes, until we get to, so those first 3, the step 1, each of those are 1 per play.
Right, okay.
And then when we get to the fan out step, where we suddenly need to do all these comparisons across plays, that's where we are generating a new channel that just takes those and deals them out to each other, essentially to make 45 tuples that we use as the new channel for inputs on similarity.
So that pairs channel, you have to sort of get the syntax. So top 100 dot combine top 100. That does is do all the combinations of
right.
And
so
a channel with 10 elements in it.
Yeah, top 100 has been defined as a channel. So what we're doing channel has all these methods on it. So I'm doing the channel method combine, and then that result is returning a channel. So that's itself a channel method dot filter, and that returns a channel. So then I operate on that channel to do.
Yeah. So at the beginning, you have 100 elements in that, and then you do the filter to get you back down to the 45. That's what the filter, right. Because otherwise you're comparing everybody against itself and all pairs in both orders. And so you want to filter that down to just pairs of things that are not the same and only one copy of each, which is what the filter does. And then the map is just sort of changing the type of it into a tuple.
Right. So imagine it as, we have these outputs for everything. There's a giant list of each play has a giant list where it's a word and how many times it appeared. We need to reshape that to work in our, to get to the input shape that we expect. And so we want to filter that and then map it to this tuple, because if I go back to compare plays, no, it's not smart enough. All right, plays. Lag. Oh, there we are. Okay. So once we get to compare plays, we see that the input matches what is the shape that we used with that map at the end. So we do that because we know we need these 4 inputs to make our code for the compare play step work. And all that stuff at the end is how we go from this big list of files and counts in Nextflow, process it down to a data shape that works here, basically. So it's asking you to essentially play ball with it. It's if you want to use Nextflow, these are the rules you have to follow. You have to use the syntax and use this kind of philosophy. But what you get for that is a lot more flexibility. Obviously, you get a lot more complexity that you can kind of capture if you're willing to put in the work, more or less. And it's very composable. So a lot of things. And I mentioned, there are a lot of community contributions. So if someone figures out a useful way in Nextflow to handle a complicated maybe combination of handling different file paths and renaming images or something, they can contribute that, and it's really easy for you to just use that as like a plugin or an import. So I've tried to write everything myself using only the base stuff to illustrate how we would use a basic pipeline like this. But in practice, and most of what we're going to talk about is that people are not writing Nextflow by hand from nothing with only the built-ins. Especially now, I would say with the advent of AI coding agents and stuff, it becomes a lot easier to deal with more complex languages and complex syntaxes because the time it takes to spin up to being able to write code that compiles and runs is a lot lower. So it's a lot easier to experiment nowadays. But even before that, the big draw of Nextflow was very much that the community produced a lot of useful things for you to take advantage of. Okay, so let me actually do the experiment that I wanted to show off in the first place. Where are we right now? Let's go up to Nextflow and Shakespeare. And let me module load Nextflow. And let me show you how this works. Let's do Nextflow run main.nf, and I'm going to say with report Shakespeare HTML. And I'm telling it to run a report for me. You can already see it's got colors and stuff, which is so beyond what Snakemake was doing. It's so advanced, obviously. And it's doing some nice stuff, like not just dumping hundreds of lines of stuff. It's actually doing carriage returns to replace things, and so it's a little nicer, right? There's more software engineering that has gone into this, obviously, but essentially it is giving us a running tally of what tasks are running, just as before in Snakemake, and it can it'll show us what's happening as it goes. These hashes that are showing up on the left, failed to render report. Oh yeah, it probably just can't find my browser. That's fine. I have one I baked earlier. So the hashes on the left, I'll explain how the work directory works, but basically every step that's running under the pipeline gets this little hash where it's like a folder with 2 characters and then a folder with 16 characters or something that are random. But the idea is that it's fully traceable. So each of those steps that run, so each of the 10 top word steps has a folder that has the log for exactly what ran, the command for what Nextflow ran, that if you need to debug, you can just run that command directly and see how it works. And it has a copy of all the input data that it used for that step and all the output data. So when I say that, as I mentioned before, that Nextflow saves everything in the work directory and it considers it temporary. This is why, because it is exhaustive in what it documents for how things ran and when they ran. Okay, so everything finished. It looks good. I ran with the report, so let me see if I can get the report up. I should have it. That's on the wrong screen, but we're going to say that's fine. All right, so the Nextflow workflow report. This was automatically generated when it ran this command, Nextflow run main.nf. Let me see if I can make this light instead of dark. Yes. So it ran Nextflow run main.nf with report Shakespeare to HTML, and it's going to give me all this nice documentation for my files. It will say you ran in this launch directory, you're in this work directory, which is where it stores all the temporary files, project directory, if that's separate, sometimes it is if it's like a sub-project. And here's the script ID, here's the workflow session, all of this traceable stuff that you can go back and use to find. It also does a lot of nice things like tell you which of my tasks in the pipeline used the most CPU usage. So count words actually used, like 60% on median of a single CPU core. It'll do the same thing for memory, which is kind of irrelevant for our tiny little text files. Same thing for job duration. They all run really fast. A really useful one for debugging why your job is slow is file I/O. When you're running on the cluster, any reads and writes from disk are going over the network for the most part because our file storage is on a separate storage node that is, in a different server rack than the compute nodes that you're running on. So if you run this and come out and see, oh, well, it's running, the clean text is reading a ton of bytes of data, that's might be something that I want to optimize. Maybe it might make more sense to preload my data on the compute node rather than have each task go out and read to the storage each time. Okay, and then you get the full table of tasks. And I think you can even, if you wanted to view there's somewhere that you can view the DAG as well, and it will render for you. But very nice built-in way to just have like a report already done of how your thing ran without having to go through and read individual log files. Very useful.
There's also a timeline that shows.
Yeah, it's like a flame chart.
I think it did like with timeline when you run it.
Yeah, you're probably right.
And then you can see sort of what's waiting on what.
Yes. Nice. Yeah, so it has, I will, there's a link at the end to like all the documentation for Snakemake and for Nextflow. Nextflow's like reporting documentation is really cool because it has a lot of really cool tools that people have contributed that help you debug and optimize your pipelines.
One thing it said 76 jobs. The Snakemake showed 77. I'm just wondering.
Oh, interesting.
What's that one?
I would guess that Snakemake counts the rule all as a job, and Nextflow doesn't use that same like construction to track what needs to happen first. So it's probably just classic off by one error. Happens all the time. All right. So let's talk a little bit about how people use Nextflow in practice. So I showed how I would translate the Shakespeare Nextflow to Nextflow, Shakespeare workflow into Nextflow. And if I was asked to do something, much more complex than Shakespeare, and I could start from scratch on it, I probably would use Nextflow. But for the most part, people actually running on real data are almost always using an existing community maintained pipeline. And there are some very good reasons for that. First of all, a lot of the workflows that people use these kinds of pipelines for are very complex. They have a lot of steps, and there can be a lot of, you could spend an entire year just drilling into each step in the pipeline, making sure that each of them is following the correct best practice and it's well documented and you understand what arguments and options and knobs to turn and tweak for each thing. Or you can stand on the shoulders of people that do this every day and who are experts in the pipeline that you want to use for a certain tool, and look at all the documentation and explanations that they have already tested and optimized and written for you. So essentially, for a lot of these pipelines that are well-formed and well-maintained, you provide your data, you learn enough about the pipeline to figure out what parts you need to use, how they work, how to configure them. You provide the options, and the Nextflow will handle the rest for you. So when we talk about configuration, we had mentioned that there's a couple places in Snakemake where you can drop in and give a configuration where maybe this rule needs to be using 8 gigs of RAM instead of 1, or I want to run when I run this job, I want it to be using Slurm for the Snakemake jobs. In Nextflow, everything is passed when you start the pipeline by a nextflow.config file. And it allows you to define a lot of things. First of all, this is still in Groovy format, I think, but it's a little more of a just like a config file, like you might be familiar with in like JSON or YAML, where it's less writing code and more just collecting values. You can define different profiles to have sets of options that make sense running in different places. So I could have, for example, a local profile that says, okay, well, running locally, there's no limit to the jobs that you can run. There's no limit to how many tasks you can run at the same time. It's all up to how many CPU cores you can use. And let's say you're limited to 8 or whatever. Versus a Slurm profile might say, okay, well, now we're on the clusters. We have this many jobs we can run an hour. We have this maximum job time, this maximum job limit in the queue, and so on. And so it allows you to kind of configure this separately for each different context you might want to run your pipeline in. You can also do some config of how it handles things like Apptainer. So usually we'll say, yes, use Apptainer. If there's container defined, download it. I usually like to say, download any Apptainer images to my Scratch directory, because it's, they can be large. They contain entire, systems basically. And there's a docs.
So if you want to define how much memory to use, where do you put it? Put it in the configuration?
So I'll show we have this this page on our docs that actually contains a good example of a full config file that I'm breaking them down here, but I want to show you the full file. So basically, all together, you can do things like, let's say I wanted to say all my resource limits, the maximum that it should ever request, meaning no matter how much my pipeline is asking for, the maximum memory you can find on a node on our cluster is this. The maximum CPUs I want you to run is this. The maximum time should be this, 1 week. And then you can add some additional logic. So something that I like to use is an automatic check based on the task to see what queue we should submit it to. So if it's longer than 24 hours, then send it to the week. Otherwise, if it's going, otherwise send it to scavenge. But if it's been interrupted on scavenge for 3 times or more, then just submit it today. So you can still add logic like this. And this is what I put on the docs to kind of give an example of what some good practice would be if you want to try to maximize how many tasks you can run. When you want to do specific things for specific processes, you can use a labeling system. So in each of our tasks, the processes that we write up in our main.nf file, we can also add labels. So if I had a process that said it has a label called process GPU, and then this config file says with label process GPU all of these options, then when Nextflow runs my pipeline, any of the processes that have this GPU label on them are going to get these options. So that I can say, okay, well, I need to use GPU. Let's say it's not super VRAM intensive, so I'll use a RTX 5000. And yeah, maybe I want to use 32 gigs of RAM and say that runs for 24 hours. All of those might be overkill for the CPU bound tasks. But if I just label the GPU processes with that label, it will automatically know that it needs to use those resource requests when it's asking Slurm for them.
So that's two separate files. The main, so you have a main.nf. So that's in that file, you define the workflow, right? What analysis you do. And in
So we have here our main.nf. And then for Shakespeare, I didn't actually write a custom Nextflow because the default is fine. But when we go up to our NF core example, which I'll do in a moment, we have both our nextflow.config, and then we have our actual script that we use to run, and this is what we're calling Nextflow. We'll get to that in a moment. So usually each time you run Nextflow, you can pass. So like if I had just done, Nextflow run whatever it was, my main.nf. You can always pass this -c option that gives a nextflow.config file. And so you can specify that at the time that you run Nextflow. And if you have it in your directory and you don't specify it, it will typically look for it and use it if you have it. So I usually, and if you read through like our docs, I recommend that you set up this kind of like default config file just to have like best practice, how many limits to jobs and things like that are always applicable on the cluster. And then if you need a job specific config file, you can also write it and pass it when you start the job. All right. All right. So I had mentioned with Snakemake, we have a pretty similar setup for using containers. Snakemake, very, very straightforward. We just say under each task container, use this container. Looks almost the exact same in Nextflow. We'll say container and use, in this case, I use the exact same container from before. It's this BW8 liner. And now it knows that when it goes in and actually tries to run this task, it's going to first pull this container, run everything else in the script block inside the container. And just as before, if you have a local container that you've built, a local Aptainer image in a SIF file, you can do the same thing where you just pass container and then some path to the SIF file. So I mentioned that you can either use nextflow.config to set up Aptainer to run always, or you can use a profile. So if you run profile Aptainer when you're starting a pipeline, it will know that you want it to pull all of the container images and store them and run each specific task inside the container defined for it. By default, when we use the nextflow.config file, I have this little Aptainer block config that says Aptainer is enabled and it auto mounts, meaning it just makes the directory you start in available inside the container, which is good to access your data. But otherwise, you can just use the profile Aptainer to turn that on.
Could I throw in one? So this is like one of the hardest things in my mind about using Nextflow is the configuration. It'll pull configuration files from a lot of different places with different precedences, as you might expect. But it took me a long time to figure out what the heck this profile thing was. And it turns out it's actually really simple. It is a filter on your config file. So what it's going to look for is something named an entry in your config file named Aptainer, and it's going to pluck that out and use it. So it's actually not. It's separate from a config file. It's really like a filter being applied to the configuration. And it took a long time for me to figure that out, and it was really mysterious until I did. So just mention that.
Thank you, Rob. Okay. Not actually plugged into power. You have it. Do you have a USB-C to USB-C? Sorry, I should have.
We need the effort. If we want to
continue,
we need the effort.
Thank you.
Thank you very much.
Appreciate that, everybody. It's the one thing I forgot. Appreciate you. Crisis averted. So I had mentioned real briefly that you can set this cache dir to scratch storage. That's a really common way people fill up their storage quotas. They just have, Nextflow downloading these like 6+ gigabyte images to their home directory, and then things start breaking. And that should already be configured when you use the profile under NF Core. So where does all this actually happen? I had mentioned when we were running things over here, we saw these hashes popping up for each of these tasks that run. And Nextflow stores every intermediate file in work. And the way that it's organized is each task gets a unique subdirectory, which is hash-based, meaning it's unique for the actually don't know what it hashes on. I think it's the name of the hash.
No,
it's
I
not the
actually
name.
found out. It's actually interesting. It hashes every part of the contents of that directory that matters in terms of the run. So that's how it figures out if something has changed. When
it's like a hash of hashes. Yeah.
Yeah. So right. So it's not just a random hash. It's when it goes to run a thing, if when it rehashes the stuff, it matches what's there, that's how it knows it doesn't need to rerun that task.
Smart stuff.
Yeah.
Very smart.
Does that mean if you change the content of that folder?
Yeah, then it'll rerun it. Yeah, absolutely.
Yeah.
Which is kind of what you want.
Yeah.
Yeah.
So the difference.
If I just add another file.
Well, you shouldn't really be doing that in there. That it's a work directory,
Okay.
Yeah.
So yeah.
Yeah, essentially it is when it starts the pipeline, it's going to it starts a task, it's going to copy what it needs, the input data for the task, to the work directory. In Snakemake, when we ran this, we changed a data file, right? And then we reran it. Snakemake is only looking at like the change time or the edit time on the data file. It's not actually doing anything to check on the contents of the data file. It just knows that the file has changed. It doesn't know how it's changed. Nextflow, because it copies everything to the work directory and then hashes everything, it knows specifically that the contents of that file has changed. So it's not just that you made a new copy of it for the new data directory. It knows that the contents, the actual data in that file has changed, and it needs to rerun some things. So it's a slightly more, I would say, robust way of like capturing when things change and when you need to update tasks in the pipeline. Okay, so inputs in this case are symlinked in, meaning they don't actually exist on the disk in this location. It's like a shortcut to where the input file is. It does that so that you don't suddenly balloon multiple copies of your giant, 800 gigabyte data files. But the outputs are actually written. So the outputs do get written to the work directory. I had mentioned that there's that special flag called publish dir, that you use when you want to copy results out of the work directory to somewhere for your final actual delivery. The work folder gets very large, so I usually either have it in the config, or you can run with this -w flag to put it in your scratch folder. Otherwise, it will, it'll fill up really fast. Like a single run of RNA-seq with like some pretty normal amount of samples it was like 168 gigs or something of storage. But the philosophy on Nextflow side is like we'd rather be exhaustive than miss something that is useful for you debugging your pipeline when it fails. So, they figure storage was cheap, which was true for a long time. Okay, so Nextflow also has -resume. So because of all of that hashing that happens in the work directory, we also know if the output isn't there, we can finish it. If the output is there, we have already done it. And if the inputs haven't changed, we don't have to rerun it. So that means we get a resume feature for free, essentially. But this is obviously a huge deal, because if you're running a really long pipeline that has 200 steps and it fails, 10 steps before the end, you really want to be able to just finish those last 10 steps and not worry about the ones that succeeded. And as I showed with the Shakespeare thing, you can also just change one process, meaning change the code, not just the input data, but change the code that runs and rerun only the things that influences to update the pipeline. Finally, when you're finished, Nextflow clean-f deletes all of the work directory. So if you know that you're done with your run, you just want to clean everything up, delete the data, you can do that, or you can store it in Scratch and have it automatically delete after 60 days. Question?
Yeah, so I work a lot with workflows where I want to automate part of it, but then there's a step where I need to manually curate something, and then the pipeline is supposed to resume. Is this function something that would do that? Or because I'm changing the files that it output from the first part, would it then try to rerun? So maybe this is not the right function then.
That's a good question. The question is, if you have a pipeline where you have maybe a number of automated steps and then a manual review step before another suite of automated steps, should you use the resume function for this, or is there a better way to do this? I would usually treat that, if I was designing it, I would treat that as two pipelines. One pipeline is everything up to your review step, and then when your review step is finished, you launch the second pipeline. It may be, and you can certainly do that in an automated way, where maybe you have some code in the Nextflow pipeline that when it's the last step of that first pipeline, and then it will, email you what you need to review or something, and then maybe it can pick up when you save the files that's ready for the next part. But for the most part, I would logically separate those as two pipelines with a review step in the middle. Okay. All right, so let's talk about the main reason people are introduced to Nextflow in the first place, which is a community of pipelines largely for life sciences called NF Core. So this is a community that has sprung up from a number of practitioners. That's open source, so it exists mostly on GitHub. It's 100 plus, probably more than 200 now, curated Nextflow pipelines, largely again for life sciences. It's a standardized structure, which means every pipeline is essentially a template of a sort of meta pipeline that is organized in a way that everything else follows. So all pipelines are containerized, meaning every software dependency has its own container. They're all tested, documented by active maintainers. So certain people are responsible for certain pipelines. There's academics that are in charge of like the RNA-seq pipeline or like the SERIC pipeline. And they have a really slick website that allows you to go browse pipelines and see them and see how they work and what their options are. So when you go to that website, and it's nf-co.re, it looks like this, and it has this huge browser where you can search all the different pipelines. And by default, it sorts by the number of stars on GitHub as like a proxy for popularity. And when you open a pipeline, it will show you all these tabs. And so this is how they're all documented in the same way, where you have an introduction to introduce you to one of the pipelines. You have these nice little like subway charts that show the different processes and how your data flows through the pipeline and what's done at different steps depending on the options you select. And then it has instructions for usage, all the different flags and parameters, the type of output you can expect. And then importantly, each pipeline is also versioned so that for reproducibility's sake, you can also pin the version of the pipeline you used. And when you pin the master version of, say, the RNA-seq pipeline, everything below that will also be pinned to a specific software version. So if I pin version 3.23.0 of RNA-seq, I know that anytime you run that version, you're getting the exact same aligner that I use, you're getting the exact same adapter trimming, all the component tools are exactly the same and fully reproducible. So why should you use these pre-built pipelines? For the most part, it saves you from reinventing the wheel. They're tested by hundreds, thousands of users, all completely open source. They're reproducible out of the box. They use containers and pinned versions for really robust reproducibility. Saves development time. You don't have to worry about the best way to do the QC of your FASTQ files. You just follow the suggested best practices and read what you need to do to configure it for your files and focus on the experiment. And they all have a very consistent interface, meaning you run them all in very similar ways. You do Nextflow run nf-core / the name of the pipeline. You can set up a profile if you're running a test or Aptainer or Slurm, like Rob pointed out, anything that shows up in your config file, you can activate here. And then you usually pick like an out directory and any other options that you want to pass.
Maybe throw in one thing. So one of the rules is when you have one of these, when you submit one of these, or the supported one has to support this test profile, and the test profile has to have a small input set. So essentially, you should be able to do a test run of any of their pipelines and not have to worry about any of the software or any of the input set for a simple test, which is fabulous, in terms of getting started with a new pipeline.
Yeah,
literally all you need is this command line and you're ready to go.
Yeah, it's really great because let's say you wanted to learn how the RNA-seq pipeline works. You would do Nextflow run nfcore/RNA-seq profile test Aptainer after results, whatever. It would run really quick because I think RNA-seq's test profile is like 40 megabytes of yeast DNA or something. So it runs in like maybe 10 minutes max. And then you can go into the work directory and it's separated by each step in the pipeline. You can see what settings for like bigwig were used, or the alarm star or salmon or whatever all the individual tools may be. You can see how it was used and what was used to configure it, and essentially how they all wire together to make the final output. So it's kind of like the way that the pipelines are designed, the reason they use that master template that they are all built on top of is that it's kind of self-documenting in a way. It allows you to start with no real knowledge of how the pipeline is organized and investigate how a test set runs and see how that would match and not match the data that you need to run it with. So I mean, we're talking about RNA-seq a lot because this is the most popular nfcore pipeline. It's for bulk RNA-seq analysis. In this case, the steps are, it runs FastQC for a read quality check. It does adapter trimming. It runs star to align to a reference genome, uses salmon for gene expression, pseudo counts, and then it does the multi-QC at the end to aggregate everything into one report so you can see how your samples did. And the test profile is just, like I said, a small yeast data set of 50,000 reads. So usually the pattern that I suggest and see most often, use most often on the clusters is like we did in the last example for Snakemake. We submit a Slurm job that starts the Nextflow pipeline. So here I have just some SBatch set up to say, all right, well, the pipeline itself, meaning just the overhead, just Nextflow managing everything, needs, let's say, 2 CPUs, 4 gigs of RAM. Let's say this pipeline takes 2 hours. And then in the script, we're actually going to run Nextflow run nfcore RNA-seq. Here we'll pin the version. We'll say profile test and Aptainer. We'll pass a config file, and we'll give it its output directory. And then when we use SBatch to submit this script as a Slurm job, this head job that we started will then submit Slurm jobs for each of the sub-processes, like we did in that example in Snakemake. It knows that for each of these sub-jobs, I want to submit its own Slurm job. Now, of course, that means that if you have, as we did in Snakemake, jobs that don't make sense to run in Slurm, well, you can also use the same filtering in your config file to swap the executor to local instead of Slurm. So in this block, the way that I illustrate this is by default, it says, okay, well, we're going to run everything on Slurm. We're going to use the day queue. We're going to use 1 time, 1 hour for time. But then if we see any of these in the name, meaning we're filtering on the name of the process in our Nextflow file, so either multi-QC or custom dump software versions, which is the step that's in the RNA-seq pipeline to kind of give a big dump of all the version numbers at the end. Then instead, we're going to use the local executor. And that's just a standard like string filtering. You just write them by name and use the pipe character as a logical OR. So this is, like we showed in Snakemake, a good idea to run on the head node instead of waiting in the queue. So it doesn't take 5 minutes to run, something that takes 30 seconds to run.
So here, what does the local mean on the working node?
It means that the node that the Nextflow job manager is running on. So we submit 1 Slurm job that's pretty small, maybe 2 CPUs, that just exists to run Nextflow as like the manager. The manager of Nextflow then submits other Slurm jobs, which might need many more CPUs, much more memory. But anything that's marked local will just run on that small manager node.
So where's the manager?
It's also a compute node. It's just,
So when we run the S batch, the job is submitted to a computer node.
Right.
So that node is the manager node.
Right.
So if executor is run, it will submit job to
other compute nodes. Yeah. So that way we keep everything that doesn't need to wait in the queue, that doesn't need real amounts of resources, running as fast as possible. Okay, so let me see if I have time to run this. I may. Yeah, I'll tell you what, I'll get it started just so you can see sort of what it looks like as it goes, and then I might talk over the rest of it. So let me run one here. So let's do, we're already on a compute node. Yeah. So you would run RNA-seq 314.0, profile test obtainer, output. All right. I have to delete my output from last time, but let's see what it says. So Nextflow starts up. It's gonna say, okay, I found the workflow you're talking about. I know that I'm going to download it from github.com/nfcore/RNA-seq. And it's gonna throw some errors, rather some warnings. It says you have, competing config files in this case. That's fine. You have some old parameters. Now in this case, it's making this full list of everything that is in the RNA-seq pipeline, and everything that's blank in the brackets and to the right means that it's downstream enough that it hasn't started being queued yet. So it's the manager has gone in and actually only ID'd things that need to run first. So just like how Snakemake before generated the whole graph of everything, Nextflow is doing the same thing here. And it's telling us, okay, well, only these first things in the graph need to run. And we'll start submitting jobs out for these. And this is what it's doing now. So it's setting up some stuff where it needs to pull these obtainer images because we've set it to essentially run every single step in a container for maximum reproducibility. So this will take a few minutes to run. You can see that some check marks are popping up now. But essentially, once this is all done, you'll have this whole output directory that you can look at each of the individual steps, as well as the final output that is produced at the end of the pipeline. And while that cooks, I will go back over here and try to finish up the slides. Okay. So when it does finish, we'll have an output directory, and it looks something like this. So for each of the major steps in the pipeline, it has a subdirectory for it. So multi-QC is like the HTML summary at the end. Star Salmon is for the alignment quantification. Fast QC does the original QC of our reads, trim galore, pipeline info, all the sort of metadata and retrimming stuff. So when this finishes, we'll have this nice HTML like report that ran automatically for us. I want to see, I might actually have one saved from before, like Julia Child. Do I? I think I do. Still have it from last time. And then let me see. I'm not used to working on 3 screens simultaneously. 360 degrees around my head. Okay. Okay. No. All right, I may have to give up. All right, I'll do that at the end when I have a second step aside and pull it up. But essentially, anything that you want as an output, you just tag as output, and then it organizes it nicely for you from what step it came from. This is a really nice thing to have because giant pipelines that have like dozens of steps, if everything's dumping into the same output directory, it can get really messy really quickly. So it's nice to have everything already organized. So NF-core is awesome. For whatever reason, I don't really understand this. Life sciences is like super collaborative in terms of posting and contributing pipelines in Nextflow and also to a lesser extent in Snakemake. To some extent, astronomy likes to publish Snakemake pipelines. They haven't quite started using Nextflow yet. It's much harder to find things for like physics and engineering. But for the most part, they people will still publish their code and publish their pipeline publicly. It's just that you may have to search in GitHub for them directly rather than like there being like a centralized community or centralized repository for them. But for the most part, there is, so there's pipeline catalogs. I would go here for Nextflow pipelines, this NF core pipelines page. And Snakemake has its own catalog, which is on snakemake.github.io/Snakemake workflow catalog. And they have kind of, analogous pipelines for everything that I've shown in the Nextflow side. If you would rather stay on Snakemake, it's, probably has a little less fanciness to it, a little less advanced features, but it's a hell of a lot easier to read and use. Okay, so I want to just quickly collect some resources and next steps here. Nextflow NF core documentation, really awesome if you want to dive deep into anything specific to one or the other NF core pipeline. There's people write really good guides on sort of how everything works and what all the different knobs mean. Nextflow has its own little training site, which is very useful because it's a very complex piece of software. So there's a lot of different tutorials and sort of seminars, YouTube videos, and documentation that you can read there. Similar for Snakemake. And then, of course, I highly recommend that you check out the YCRC's HPC documentation, which is what I was reading from over here. We at YCRC spend a lot of time writing documentation pages and trying to capture the questions people have most often and make sure that they're available on our doc site. So we also have office hours every Wednesday at 11 and Thursdays at 2. So you don't need to make an appointment. You can just drop in. We have a link to the Zoom on our website. But if you can't make it to office hours, you do want to have some questions or a problem that you're running into. We also do consultations by appointment. You can shoot us an email and we'll set up a Zoom meeting and basically just work through a problem with you. And that's also totally free to you. All right. Finally, last thing is, all right, well, now the screen seems to have frozen right when I was about to get to my feedback slide. So,
Convenient and
how convenient. I had one slide left, and it's the QR code that has like the feedback survey, and I don't know why all of a sudden. Oh, hey, there we go. Okay. Great. So thank you everyone for today. Please feel free to scan this or click the link if you're on the GitHub that has the PDF of the slides. Quick 2-minute survey. It's anonymous. We just ask you to rank how useful you found this workshop. And yeah, that's all I have. If there's any remaining questions, please come up to me. Raise your hand. We still have 15 minutes or so on the slot. So, and beyond that, I'll just use the remaining time for any ad hoc help, office hours, questions, etc. So, thanks for being a good audience.
Sam, do you think it'd be useful to show one of the work directories and just point out what the components are? Because
yeah,
in terms of debugging, that's a really hard thing for beginners, and understanding what's in those directories is really helpful.
So we have one running here where it's gonna be kind of annoying to do here. It's slightly smaller. Okay, so let's take a look at one that has finished. So this is one of the, okay, so there's one of the steps here that's in, it says it's stored in A2/81F1. Okay, so in the work directory, it's organized by these hashes. So the first one that we're looking for is A2. And of course, letters come after numbers. Numbers come after numbers. Okay, so we're gonna go to A2. 81F1. Okay, so this is the work directory for this specific step. that we saw, which appears to be some subsampling step of salmon, the read count aligner. And in here, there are a bunch of different command like files. So let me shrink this. And so first of all, the command.sh is the exact command that is being run in this step to produce the output. So you go in here and you can see exactly the code that Nextflow is using to run. And it's saying, okay, we're gonna run exactly on this file. That's like your input file. It's using these arguments for the tool that it's calling. And then it does some nice metadata stuff where it dumps the versions of everything into this YAML file. And then it probably prints something to the log. You can look at the log file, the command.log, which is the actual standard out from running that command. It splits the standard error over to the .err file so that if there were any error files, it would show us there. And then output, I think, is just the combination of standard out and standard error. Command.run is the full actual submitted to the scheduler script. So if we look at, it's a good way to illustrate this. Scroll the map. Why would it? Okay. So basically what you're seeing here is that Nextflow is generating for itself when it actually submits a task, a full, its own mini Nextflow file that contains everything that it needs to set up this task completely independently. So it's doing this in a very automated way, which is why it can have all these additional functions and useful things for it. But basically it means that if you ever wanted to go back and run just this task alone, you could just run this command.run file and it would run in a Nextflow context in the exact same way that it ran when it was part of the bigger pipeline. It's, trust me, it's useful for debugging. It's a lot easier to start with just a very small reproduction of whatever problem you're running into than try to freeze the whole pipeline at the exact right point and pause it and debug it where you ran into the problem. What else we got? Anything else we should cover, Rob?
Highlights, yeah. I mean, this one is really hard to read, but as Sam said, it's very nice for just reproducing the run. And also, it can be very useful for figuring out how you misconfigured your configuration files. Because if you stare at it, you'll see what it's actually doing in terms of how it ingested your configuration and turned it into stuff.
Yeah. So that's it. That's that's Nextflow. I think Nextflow understands, the Nextflow developers understand that it's a really complex tool that's hard to wrap your head around everything that it's capable of. So they tried to build in, pretty good debugging tools and investigation tools to help you with that. So yes. Thanks.